Hi, this is Maziar Foroutan, a Ph.D. student from the University of Vermont. In this project, I have worked under the supervision of Dr. Ehsan Ghazanfari and Dr. Maziar Foroutan from the University of Vermont. The title of my presentation is Geo-statistical evaluation of the intelligent compaction performance in reclaim-based projects. This project was performed in Vermont. First of all, we are going to go through what you should be expecting to see in this presentation in the slide of presentation outline. This presentation starts with a brief introduction on IC technology. Then we will get a little bit familiar with the project details and the methodology being used to evaluate the compaction consistency and uniformity, and at the end we will see the results of the geostatistical analysis and the conclusion section. Intelligent compaction. So intelligent compaction is an innovative technology which is intended to improve the consistency and uniformity of the compaction operation. The roller in this case is equipped with GPS and accelerometers, which is connected to a control unit, and using these features, the IC operation can provide us with real-time compaction measurement values, which are also known as compaction meter values, CMV, or ICMVs. Here are some of the advantages and disadvantages of IC. One of the most important advantages is that IC can provide us with information from the whole compacted area. And the second one could be that IC can avoid extra roller passes, and we can be kind of sure that we have gotten the optimal number of roller passes. And if the IC technology is appropriately implemented, it can serve as a better QA tool, and it can potentially improve the compaction consistency and uniformity. But there are also some disadvantages associated with using this technology. And the first one is that, and this is the one that we have seen in Vermont, was that the majority of the contractors and some of the state officials were not familiar with this method that can be potentially problematic. And the second disadvantage is that the uncertainty in the correlation between ICMVs and spot test measurement, in which our previous studies and some of the studies in the literature have faced very weak correlation between these two measurements. And also, for compacting the asphalt layer, there is a huge uncertainty among the ICMV values, which again could be because of the non-homogeneity of the material, which increased on the asphalt layer. So now we want to go to the slide that we talk about the project details. So initially, 4 inches of the distressed pavement was removed, and the remaining pavement were pulverized to the depth of 10 inches. And this was considered as the first reclaim phase, and the road was compacted using the IC roller after laying down the first reclaim layer. And then for the second reclaim phase, a 6-inch layer of emulsion mixed with reclaim-based material was injected, and the road was compacted using the IC roller, similar to the first phase. And at the end, we want to mention that on both layers, nuclear gauge density and dynamic concentration were performed, and you can see all these steps in the figure on the left. And now the methodology that we use in this research. So the main purpose of this research was to evaluate the consistency and uniformity of the compaction measurements. And the method that we used to evaluate the consistency and uniformity of the compaction on both reclaimed layers was geostatistical analysis. And in this type of analysis, we use the semi-variogram models to capture the geospatial structure of the compaction measurement data. And as you can see here, the geostatistical the semi-variogram model have three parameters: range, sill, and nugget. And in this study, higher range values and smaller sill values are interpreted as better uniformity and consistency. And again, as you can see here, there are four different types of semi-variogram model that can be fitted to the data: power model, exponential model, Gaussian model, and a spherical model. So we have used all these models in this study except the power model. And the way that we can select the model is that we would first come up with our experimental semi-variogram data points, and then we will select the model that best fits these points, these data points. So now we are going to see the results of geostatistical analysis for the first reclaimed layer. As can be seen, the semi-variogram model of ICMV NGD measurements has like kind of similar range values. The ICMV data has the range value of 48 feet, and the nuclear gauge density data has the range value of 45 feet. However, the DCPI data has a relatively larger value, which can be interpreted as better uniformity and consistency among these type of measurement. And here is also the summary of the measurements and the summary of the statistic for the first reclaimed layer. As can be seen, the range values of normalized models were identical to the range value of original model. And also you can see the relatively large sill values in icy roller measurements, I mean the ICMVs, which can be interpreted as a higher level of inconsistency among the icy roller measurements. And now similarly, we have the semi-variogram models for the second reclaimed layer. The results of geostatistical analysis on second reclaim phase also revealed that there was a better uniformity and consistency among DCPI measurements. As you can see, the range value is 83 feet, where the range value of NGD data and ICMV data were only 52 and 68. And the interesting point about the results of this study was that the range values on second reclaim phase were consistently larger than the first reclaimed layer, which can be an indication of better uniformity and consistency, which was interesting because we were expecting that in the second reclaim phase we will have lower degrees of uniformity and consistency because we were kind of adding to the non-homogeneity of the material. And this is also the summary of a statistic for the secondary claim layer. As you can see again, the range values of the normalized and original semi-variogram are identical. And at the end, in the conclusion section, we have the first conclusion that which is very important, is that the spatial structure of the compaction measurements was successfully captured. This means that we kind of proved that the compaction measurement values that are closer to each other are more statistically dependent compared to the compaction measurement points that are farther from each other. So this is very important, and this is the foundation of future research that we are going to perform in this area. And the higher range values during the secondary claim phase can be inferred as higher degree of uniformity and spatial continuity. And also dynamic cone penetration data showed higher range values, which this again means that there was a higher level of uniformity and spatial continuity compared in these type of measurements compared to IC roller measurements and nuclear gauge density measurements. Also, the higher level of inconsistency in IC roller measurement, which we saw that we have relatively larger seal values among the semi-variogram of IC roller measurements, could be because of the non-homogeneity of the underlying layers, and also the variation of the frequency and amplitude during the compaction operation. And this study is actually the foundation of future studies and future research that can potentially help the Department of Transportation to develop regulations and standards for acceptable level of compaction uniformity. This means that we are planning to kind of quantify the compaction uniformity and consistency using the experimental methods and also the geostatistical modeling. And these are the references that we have been using in this study. And at the end, the research team would like to thank and appreciate the Transportation Infrastructure Availability Center (TIDC) and also USDOT for supporting this project. And thank you for your attention.